The solar system is filled with things that could go horribly wrong. Comets zooming past Earth, asteroids crashing into planets, whole dwarf planets getting flung out of orbit. But sometimes, just sometimes, everything comes together and it's really beautiful. And that's what we're talking about today. This is Janus and Epimetheus. They are Saturn's moons, and they do this, swapping orbits once every 4 years. It doesn't even look real. It looks like someone paused the simulation, but it is happening in real time. And to be clear, they are not orbiting Saturn here. They're just passing by each other. They're actually orbiting the Sun. It's hard to talk about something being graceful when there are giant planets and moons just flinging themselves around the Sun at 27 kilometers per second. But these to make it work. Their orbital dance is perfectly balanced. They never collide despite being only 500 kilometers apart at times. And they are stable. This won't end in a catastrophic collision for millions of years. And that raises a question. How long can such a fragile system stay stable? We don't know the answer to that yet. It all depends on how well we understand the forces that keep them dancing. And to get to that understanding, we have to take a closer look at their steps. Janus and Epimetheus are what astronomers call co-orbiting moons. They have similar orbital periods. They basically take turns leading the dance, taking the inside track where it's closer to Saturn and passing the outside track every few years. And the reason they do and collide when they pass each other is that they have slightly different speeds. When two objects orbit the same planet, the gravitational pull of that planet keeps them in a synchronized formation. In this case, Saturn's gravity keeps them locked in a stately promenade. Now, because their speeds differ slightly, their orbits aren't perfectly aligned. That means that one moon always has to catch up to the other. And when they do, they perform an elegant little exchange. In reality, it's more of a gentle nudge than a full swap. Janus doesn't just bump Epimetheus all the way back to its original starting point. Instead, they both change their paths a little bit, kind of like when two skaters spin around each other and then break off in new directions. But you might notice that their choreography isn't completely random. The moons don't just move in any direction after their little nudge. There are constraints, rules, or limits that define what moves are allowed. And those limits come from the overall energy of the system. Think of it like a spinning figure skater pulling their arms in to spin faster. The tighter the orbits, the faster the moons move. And the wider the orbits, the slower they move. If either moon were to speed up too much, its gravity would pull it outward and it would fly away from Saturn. If it slowed down too much, it would crash inward and burn up in Saturn's atmosphere. And that's why their dance has been going on for so long. The motions of these moons are constrained by these limits, which keep them exactly where they need to be to stay in sync. So if you want to know how long this orbital dance will last, you need to know how fast they're moving. Now, we can measure how fast they're moving pretty easily. Watching videos of them doing their thing, we can see that they cover some distance in a certain amount of time. And if we assume they're moving at constant speeds, we can calculate those speeds. But there's a problem with that. They're speeding up and slowing down a little bit. Like right now, Janus is speeding up because it's getting closer to Saturn, and that means stronger gravity, which makes it move faster. 4 months later, it will pass its farthest point from Saturn and slow down. Over a year, the moons complete an orbit around Saturn and back again. So knowing their average speeds over a year isn't enough. To predict whether they'll stay in sync, we need to know how fast they're moving at every point in their orbits. That's called their velocity vector, which tells us both the speed and the direction of motion at every instant. And we can use that information to calculate what their orbits will look like over very long time scales. Astronomers have done just that using data from NASA's Cassini spacecraft. By measuring the position and speed of Janus and Epimetheus, they constructed a model to accurately predict how their orbits will change over time. And thanks to that work, we know that their orbital exchange will continue to occur every 4 years for at least several million more years. But that still leaves the question, how long can such a fragile system stay stable? Well, stability means something different in astronomy than it does in choreography. Stable in dance means it ends nicely, like a bow. Stable in space means it will continue indefinitely, or at least for a very, very long time. And the good news is that the system is stable. The bad news is that stable doesn't mean it can't undergo sudden changes. Like the moons might suddenly start spiraling inward towards Saturn, crashing into each other, or just getting lost forever. To tell whether that will happen, we need to zoom way out and put our planetary system on a galactic diet. I'm just kidding, we don't actually need to do any of that. Thanks to Newton's law of universal gravitation, we can predict what will happen under almost any conditions. All we need is the mass of each object and how far away each pair of objects are from each other. With that, we can calculate the gravitational force acting on every object. And if we know the force, we can predict how the positions of the moons will change over time. Now, you've probably heard Newton's famous equation, the apple falling on his head, F equals ma. That's Newton's second law of motion, which relates force to mass and acceleration. But the force of gravity between two objects isn't constant. It depends on the masses of the two objects and the distance between them. That's why there's no gravity in outer space. There's nothing to pull the astronauts toward. It also explains why the further away you get from Earth, the weaker the gravity seems. Anyway, Newton figured out that the force of gravity between two bodies is equal to g times m1 times m2 divided by r squared, where g is the gravitational constant m1 and m2 are the masses of the two objects and r is the distance between them. Now, that's Newton's law of universal gravitation. If we plug this into Newton's second law and solve for acceleration, we get another familiar equation, A equals gmm divided by r squared. Notice that this equation looks just like the equation for the force of gravity we had before, except now we've got m1 in the numerator, meaning it cancels out with the m1 in the denominator. So all we're left with is the acceleration of object 1 due to object 2, and we can do the same for the other object. We can add those accelerations together with the accelerations due to all the other objects in the solar system, and we get the net acceleration of the moons. And if we integrate that over time, we get the velocity vectors we need to model how their orbits will change. Doing that calculation reveals something interesting. Unlike the three-dimensional version, the two-dimensional version of Newtonian gravity can have strange solutions that don't dissipate over time. Solutions like this moon system, which will never decay into a spiral or scatter into outer space. But here's the twist. Although this system is stable according to Newtonian gravity, that doesn't mean it's stable according to Einsteinian gravity. You see, Einstein told us that gravity isn't really a force. It's the effect of curved spacetime. Spacetime curves around massive objects, and the more massive the object, the more spacetime it warps. When another object enters the warped region of spacetime, it follows a straight path until it hits something, and that path is what we call a geodesic. So the next step is to replace Newtonian gravity with Einsteinian gravity, throw in some numbers, and follow the geodesics. And that tells us that the system is indeed stable, at least for the next 1 trillion years or so. But that doesn't mean that we're in the clear. The results of these calculations depend on the accuracy of the measurements of the initial conditions. The position and speed of the moons can vary a tiny bit from observation to observation. And if we use the most uncertain of those measurements, the system might only be stable for a few 100,000 years. And since no one wants to live in a place that might randomly destroy itself in a few 100,000 years, I think it is best to keep checking in on the moons of Saturn and making sure we didn't miss something. After all, who knows when the gravitational rustle will show up? I recently discovered the music of a composer named Olafur Arnalds. I hope you enjoy it as much as I do.